This video is going to cover section 3.3, some applications of linear functions. Applications of linear functions are used in many different fields. That's one reason why many different fields require finite math. It's commonly used in business, medicine, computer science. Those are some of the many fields that use finite. The examples we're going to talk about today are particularly relevant to business, but they're really relevant to anything where we're dealing with money. So these are examples from your textbook, and the first is an anti-clot drug can be made for $10 per unit. Additionally, the total cost to produce 100 units is $1,500. We want to find the rule of this. This is called the cost function. This is the cost to make something. Because it's a linear function, the rule is going to look like an equation in slope-intercept form. Because it's a cost function, we call it capital C of x. The capital C is for cost. But notice that this is the same format as we've seen for slope-intercept, which is the same format as y equals mx plus b. And just like with a slope-intercept equation, remember, all functions are equations. M is our slope, b is our y-intercept. It's where it crosses the y-axis. So here it's going to be where it begins. Because remember, costs aren't going to be, our x-axis is not going to ever be negative in most business applications. What are we given? We're given that the cost per item is 10. That's our slope. That is how much it increases per item. So our rule is, right now, C of x equals 10 times x plus b. If the cost per unit had been $15, it would be 15x. If the cost per unit had been $5, it would be 5x. To find b, we use the fact that it costs $1,500 to produce 100 units. So that means that C of 100, we write it this way because we're saying that x equals 100. X is the number of units being produced. So when C is 100, that means our cost is going to be 10 times 100 plus b. And our total cost is going to be $1,500. 10 times 100 is $1,000. And then using algebra, we get that b is 500. So this is our starting cost, or our fixed costs is what they're often called in economics. This is the cost whether we make 0 units, or 1 unit, or 2 units, or 1,000 units. This is just like the cost to keep the lights on in the factory. This is the cost, no matter what, it's going to cost us $500. Then additionally, it's going to cost us so much money per unit. In Math for Liberal Arts, you might have had questions that were kind of similar to this for problem solving. Something like a car rental, where a car rents for $50 a day plus 10 cents a mile. That's the same sort of problem. We have a fixed cost, and then we have so much per unit. So our full rule, our full cost function, is C of x equals 10x plus $500, or 10x plus 500. If we were going to graph this, we would start when x is 0, so x is 0 here, we would start at wherever 500 is in our graph. So if this is 500, this would be our first point on the graph. And then our slope is 10, so that means we would go, for every 1 over we would go 10 up. So this would be 510, 520, 530, 540. If we were at 5 units, we would be at 550. I'll make a squiggle in my graph to show that it's not to scale. Again, this is our cost function. This is how much, excuse me, This is how much it costs to make this particular drug. So again, our fixed costs, that's always our B. B is our fixed cost. That is what it costs no matter how many units we make. Even if we didn't make any units, say that day or whatever, it's still going to cost us $500. So a cost function is an important function for you to be aware of. And again, the rate of change of a linear function is going to be the slope. And something like a cost function, the rate of change is the number of the cost of each unit. So it's how much costs increase for each unit. In a linear cost function, c of x equals mx plus b, our marginal cost is m. That is the slope of the line. And the fixed cost is b. That's the y-intercept of the line. What's called the marginal cost is the cost of producing one more item. And in linear functions, those costs remain the same. So if I make 100 items at $10 and the cost is $10 per item, it's going to cost me $10 more to make the 101st item. If I make 1,000 items at $10 per item, it's going to cost me $10 to make the 1,001st item. There are also linear revenue functions. In a revenue function, that represents the amount of money that the company is making. The slope here is called the marginal revenue. So revenue is what the company gets. It's not their profit. It's what they get for each item. And so that is R of x for revenue equals kx plus d. Now, for revenue functions, d is usually going to be 0 because if you don't sell anything, you aren't going to have any revenue. Now, that might, I'm going to say that could potentially vary in really complicated situations, but in general, our intercept here, our y-intercept is going to be 0 for a revenue function. So what we see here is a graph of a function that is similar to this. It's not the same function. This is one of the examples in your textbook. So here we have this example. We have a cost function, c of x equals 250x plus $213,000. So which of these is our slope? Right, our slope is 250. For every 250 up, we go 1 over. 250 up, 1 over. Now, what we're really going to do is say for every, we're going to multiply that by quite a few to get what it really is. To get something that, not what it really is, but to get something that will work well on a graph when we're dealing with such large numbers as these. And what is slope called also in this situation? Slope is called our marginal cost. Our marginal cost here, assuming these are in dollars, is $250. If these were in something else, our marginal cost would be something else. So if these were in yen, our marginal cost would be 250 yen. If these were in euros, our marginal cost would be 250 euros. If you know, whatever currency it might be. And then 213,000, that is our y-intercept, that's our b, and this is our fixed costs. So here we're saying no matter how many units of whatever it is we make, it's going to cost us $213,000. Again, that's like what costs us for property taxes, for the factory, for overhead costs, just the things that stay the same, whether we make 0 items or 1,000 items. So this, what looks blue, and if you're colorblind, it's this line that I'm trying to highlight here with the laser pointer. This is our cost function. So this shows the cost that, here's our cost if we make 200 items, if we make 400, if we make 600, if we make 800, if we make 1,000. Because this is a linear function, our slope stays the same. So it's going to be, the cost of each item is always going to be the same if it's a linear function. In the real world, that might not be true. In the real world, sometimes if you make lots of an item, your costs might go down. Or sometimes if you make lots of an item, maybe your other costs are going to go up somehow. And so in more complex real world situations, we use more advanced mathematics, including calculus sometimes, to calculate these sorts of things. What we're doing here is a simplified version of it. And then this is our revenue function, R of x. And R of x is 550x. This is what we are selling our product for. Each unit cost us $250 to make, and we're selling it for $550. So maybe we're making a new game console. And so I'm making the Atari 26,000. And the Atari 26,000 costs me $250 to make, but the revenue I get for it is $550 per console is revenue. Now that's, again, not profit. Profit happens in this blue area. This is our profit zone. This red area, or orangey area, depending on how your monitor displays it, this is our loss. So the place where the profit and the loss meet is called the break-even point. The break-even point is where the revenue function and the cost function meet. The revenue function, I think I might have said before, it's where profit and loss meet, and that's wrong. It's where the revenue function and the cost function meet, where these two lines intersect. And so that's this right here. And this tells us that we are going to start making a profit at the point when we can sell 710 units. If we sell less than 710 units, we're going to make a loss. If we sell more than 710, we're going to make a profit. At 710, we earn $0. We don't make a profit. We don't make a loss. We earn $0. How do I find this value? I find this value by setting my two functions equal to each other. The break-even point occurs when my cost function equals my revenue function. So if my cost function equals my revenue function, I'm breaking even. And to break even means I don't make a profit, I don't make a loss, I'm even. So in this particular setup, we would take 250x plus 213,000 equals 550x. And then we would solve this using algebra. We would subtract 250x from each side. And so we would get 213,000 equals 550 minus 250. That's going to be 300x. And then we will bring in our calculator and we'll divide both sides by 300. So 213,000 divided by 300 gives us 710. Then the other thing we might be asked is then how are we asked to get this value of 390,500? This is how much it costs us to make 710 items. So if our revenue is more than $390,500, we'll earn a profit. Every dollar, every cent above that is profit. But if our revenue is less than that, that's what our loss is going to be. So if our revenue is $10,000 less, we have a loss of $10,000. If my revenue is $190,500, I have a loss of $200,000. So to find this, I just am going to plug in 710. So on the calculator, I took 710 times 550. That's my revenue function. And I'll get the same result if I take 710 times 250, or 250 times 710, plus 213,000. That's my cost function. I get the same in both results. I can also find this point by graphing it, and that's what the next slide shows us. This is a calculator screen from a TI-84, I would assume. It shows the graph of those two lines and the intersection. I'm going to show you how to do this on the calculator, and this is going to be something that I think is going to be important for you because you're going to do this again for other types of problems. So I'm going to make this so it's always on top or always in front. Then I'm going to scroll back a screen so I can put in our functions here. I'm going to put in my functions as y values. I'm going to clear out what I have in here from another class. So I'm going to say that y sub 1 is my cost function. That's 250x, x. I always do that. I type x on the computer keyboard, and that doesn't take that in the calculator on screen. So the cost function, 250x plus 213,000. My revenue function is just 550x. See, I did it again. All right. Now I need to graph these. Now if I just take graph, I'm not going to get anything that's helpful. So we're going to try zoom fit, which also isn't helpful. I didn't think it would be. So the hardest thing about graphing on the calculator is setting up our parameters. So this is really good for us to talk about. To set up parameters of what the graph is going to look like, we want to go to the window button on the calculator. And because we already have a graph here, we can just use this to guide us. So x min is the minimum x value we're going to display. So our x minimum is going to be 0, and our x maximum is going to be 1,000. Scale refers to the distance between our tick marks. And so we'll use the same that it has on the graph on your screen. And so our scale is going to be 200 because there's 200 between each tick mark. For our y minimum, that's going to be 0. Our y maximum is going to be 600,000. We'll see if the calculator likes that large of a number for that or not. And then here, our tick marks for the y-axis are 100,000. There's 100,000. It goes up by 100,000. When you use window on your calculator, if you are familiar with these other ones, you can certainly use these if you want. I wouldn't worry about it though. Just set these functions. Now when I hit graph, hopefully I have something that looks a little bit better. There we go. So the point where these two cross is my intersection. That's my break-even point. That's what we found using algebra over here. We're going to find it on the calculator. So let me get this a little bit larger here, actually a lot larger. I want you able to see this well. All right, so to do this, to find the intersection, hit the second key and choose Calc. You're going to go down and you're going to choose choice 5, intersect, for the intersection where the lines intersect. Choose 5, hit enter. Now it's going to ask you a question. It's going to ask you, what is your first curve? Technically, all of the lines that we're dealing with on calculators, technically a line is a curve. So be aware that that's what you're asked. When it says first curve here, it means what's the line that you're interested in. It doesn't matter which line you choose first. Notice that at the top of your calculator screen, it will show you the equation that you entered into y equals when you entered those equations or those functions. So if you aren't sure which one is which, it tells you up there. You move along the curve if you ever need to by pushing the left and right arrow buttons on your calculator, usually. Left and right goes up and down. It doesn't matter where you are along the curve for this. Just hit enter. And then it's going to jump to the other curve. And again here, I'll just hit enter again. If it didn't jump, you can move between curve and curve, usually by pushing the up and down arrows on your calculator. You can see those flashing on the screen, I hope, as I do this. Notice again on the second curve, it tells me at the top, hey, that's 550x. That's what you put in there for y. That's also a nice way to check your work. So again here, I'm going to hit enter again. Now it's going to ask me to guess. Here's why it asks me to guess. It asks me to guess because the other time that we find intersects, we find them a lot in college algebra, in trig, and in calculus. And we're going to have multiple intersections in those courses. And so it's going to kind of ask us, hey, what area do you think it is about? We are not going to have to guess in this class because we're dealing with linear functions. So when it asks you to guess, just hit enter again. When it asks you to guess, hit enter again. And it tells us the intersection. Our intersection is x equals 710, y equals 390,500. This is going to be really helpful later in the course because we're going to find some intersections of things where doing them with algebra is going to be tricky because we're going to have decimals as part of our answers and stuff like that. So being able to graph it on the calculator is helpful. Being able to do it via algebra is also helpful. You should be able to do both. So that's this point right here. I'm going to clear my ink now from the slide. Notice how it's written here. This is written as an ordered pair, as an x and y coordinate, x comma y. You are often going to have to interpret this. So remember here, our x value is the number of things we're selling, the number of video game consoles or whatever it happens to be. That's our x value here. So we're selling 710 of them. And then our revenue and our cost, both at this point, is this. Is 390,500. That's what a break-even point means. Our revenue equals our cost. Two other types of curves that you need to deal with in this course are also related to economics. Those are demand and supply curves. I put up some optional supplementary videos that I would encourage you to look at because this comes up quite a bit and it's something that's going to show up on your final exam for this course. We use different letters to represent supply and demand. It's not ever consistent. So what your textbook is doing here is one approach. So this is our demand curve. And so our demand curve, this is how much of some unit is demanded. This is part of economic theory. Basically, for most things, as price decreases, the demand increases. So, and vice versa. As the price increases, demand decreases. So, if something, let's say I want to buy a steak. My apologies if you're a vegetarian. I don't mean to offend you. But let's say I want to buy a steak. And so the steak is selling for $60. I'm probably not going to spend. In fact, I know I'm not going to spend $60 on a steak. And if nobody else is either, that means that the demand is zero. So at $60, no steaks are going to sell. On the other hand, the price of a steak is $10. The quantity demanded, and let's say this is at a particular grocery store, or we could say that quantity is in thousands or whatever, but we'll just say the quantity demand is like 67. And if steaks are free, quantity demand is going to be 80. It's not going to be infinite. Sometimes people think, oh, if something is free, there's going to be infinite demand for it. And that's never true. There's always a limit to demand. All right. So as price increases, demand decreases. As price decreases, demand increases. So this particular demand curve or demand function is represented by this equation. It is the price is going to equal 60 minus 3/4 Q, where Q is the quantity. And so this would be an example of we have 2 points on the curve here, and we can see that our slope, again, is going to be negative 3/4. This, again, is just in rewritten format. This is y equals b plus mx. So we could also have written this as that the demand is negative 3/4 Q plus 60 is the equation of our demand curve or our demand function. We also have a supply curve. So in this case, our supply equation is defined as 0.85 Q. Notice that this does not have a y-intercept. Why doesn't it have a y-intercept? Well, because if the price of something is 0, no one is going to make it. Right? If the price of apples falls to be $0, farmers are not going to grow apples. So if price of something is 0, the supply is also going to be 0. So the supply curve usually has a y-intercept of 0. As price goes up, the quantity available goes up. So if apples are, the apples are going for 0, let's say $0 a bushel. No one's going to buy no one's going to make apples. No one's going to grow and sell apples. If it goes up to $10 a bushel, and I don't know what apple prices are, I'm pretty sure they aren't $10 a bushel, but pretend that they are. If it go up to $10 a bushel, then a few growers are going to start growing apples. If they go up to $20 a bushel, even more will. If they go up to $30 a bushel, even more will. If the price goes up to $60 a bushel, we'll have almost 70 bushels being supplied. So as the price increases, the more companies are going to produce. So as price goes up, supply goes up. This is the opposite, right, of the demand curve. The demand curve, as we saw, is that as price goes up, demand goes down. That's why the demand curve slope is negative. The y-intercept of our demand curve represents at what price demand is 0. What is too expensive? What would price you out of the market? When we put these two curves together, we see how supply and demand interact. This point right here, where these two lines intersect, is similar to our break-even point for our revenue and our cost function. This is what's called the equilibrium point. This is where supply and demand meet. The price is low enough that people are willing to buy, and it's high enough that people are willing to produce. If the price is higher than this, there's going to be more supply than demand. If the price is lower than this, there's going to be greater demand than there will be supply. Now, all of these graphs come from your chapter. They're all about one particular example. Every industry, every item sold has different supply and demand curves. And if you take classes in economics, you'll learn things like this is going to depend on whether an item is considered a necessity or a luxury. It's going to depend on other things as well. It varies from item to item, from good to good, of course. This dashed line you might be wondering about if you haven't read your textbook yet. This was a question asked in the example. If the price is $40, is there going to be a surplus or is there going to be a shortage? So if the price of whatever it is we're selling, the price of a bushel of apples is $40, our demand is going to be right about here. Our demand is going to be about, looks like 27 or so. Our supply at $40 is going to be about 47 or so. So there is a surplus of goods here. There is a surplus of supplies at $40. But if we're at $20, that's going to be here almost the opposite. At $20, we have a supply of just over 20 bushels of apples. but we would have a demand of over 50 bushels. There would be a shortage. So some people think that lower prices are always better for consumers and higher prices are always better for producers. That's not true, because if prices are too high, there's not going to be enough demand and there's going to be a surplus. If prices are too low, there's going to be too much demand and there won't be enough supply, so there will be shortages. So the ideal, theoretically, is something that is at or very close to this equilibrium point where supply equals demand. So again, I hope you'll take a look at some of these, some of the videos I put up. I tried to give a relatively brief introduction here. I know it's a half hour, so it's not that brief, but I'm trying to give some points of a semester plus economics courses in one session. So I hope this helps. Please look at these applications in 3.3 really carefully, because you are going to need to work especially with supply and demand. And again, be aware it's not always, the letters we use aren't always the same. So you have try to understand the concepts underlying it, because sometimes how it appears might look just a little bit different. So the rest of this chapter is optional. There might be some things I assign. I think I asked you to maybe read a few pages elsewhere in the chapter in the notes. That might be in chapter 4 though. Be aware that if you're transferring this course to another institution, some institutions expect you to be able to work with things like quadratic functions, polynomial functions, and rational functions. If that's the case for you, you should definitely do those sections in MyMathLab just as part of the study plan, so that you're prepared for future courses. And remember that those future courses aren't necessarily math courses, because much of what we do in finite is applications that are used in business, in the natural sciences like biology or physics, especially biology, I think, or in the social sciences, whether it be sociology or education or something else. So it's not necessarily going to, you might say, well, this is my last math class, but you might want to look at if you know your transfer institution or what other classes you're taking there at your bachelor's institution, and take a look and see, you know, does it look from their course description like they expect you to know some of these things that we don't specifically cover, but that some finite math courses at some institutions cover. So be aware of that. If you have any questions, please let me know. Please, again, take advantage of the tools you have in MyMathLab.